Okay, then how to show this theorem? So let Gix is equal to Fix minus Fi x star. Here, of course, x star is the optimal point of total function f. So x star is argmin of fx minus gradient of Fi x star transpose x minus x star. Okay, so the meaning of Gix is this. So this is Fix function, and for Fix function, x star is not the optimal point. It could be optimal point, but in general, the optimal point of Fi and the optimal point of the total function, capital F function, different. Okay? So this is the optimal point, and when you drew a tangential line at point x star, maybe we have this kind of affine function. And the Gix is the difference between Fix and this tangential line. Okay? Right. Then Gix is minimized at x star. Why? Because the difference between Fix and the tangential line is 0 at point x star, because this is the tangential line defined at x star, and the difference always positive. So we can say that Gix star is equal to 0, and this is minimum point. So we have Gix star is equal to 0, and gradient of Gix star also equal to 0. So from this property, 0 is equal to Gix star. This is since x star is the minimum point, this is less than or equal to mean the step size eta Gix minus eta gradient of Gix. From beta smoothness, the Gi function is upper bounded by minus eta gradient of Gix transpose gradient of Gix plus beta over 2 eta gradient Gix norm square. This is minimized when eta is equal to 1 over beta, and this value is Gix minus 1 over 2 beta gradient Gix norm square. Okay, this comes from beta smooth, and this comes from the optimal step size 1 over beta. Okay, so we can say that gradient of Gix norm square is upper bounded by 2 times beta times Gix. Okay, so gradient of Fix minus gradient of Fix star norm square is upper bounded by 2 beta Fix minus Fix star minus gradient of Fix star transpose x minus x star. Okay. Why? From the definition of Gix ix, gix was fix minus fix star minus gradient of fix star transpose x minus x star. When you take the gradient here, since this is constant, you can remove this. And this is an affine function with respect to x. So, and this is just slope. We can remove this part. So gradient of gi is equal to gradient of fix minus gradient of fix star. Okay, so when gradient of fi norm square is upper bounded by 2 times beta times gix, from this and the definition of gix, we have this. This is definition of gix. Okay. Right, so up to now we have just some obvious inequalities. And also we have gradient of fx star is equal to 0 because x star is the optimal point of the capital F function. Okay, so from this, when you sum up all the gradient of fix minus gradient of fix star norm square, like this, from the previous inequality, we have 2 beta times sum I want to n fix minus fix star minus gradient of fix star transpose x minus x star, and the sum of gradient fix star is equal to 0. We have 2 beta times the total function fx minus fx star. That's it, because the gradient summation equal to 0. Right? So let's say Vt is equal to gradient of fit xt minus 1 minus gradient of fit x tilde plus mu tilde. That is the gradient update by one iteration of SVRG. Okay. And now I will show that the variance of Vt is upper bounded by something, and the something converts to 0 as the number of iterations grows up. Okay. Since the variance is very hard to deal with, I will use the norm of Vt square. Essentially, the norm of Vt square, the expectation of norm of Vt square is very nice upper bounding factor, upper bounding value of variance of Vt, because the expectation of square always greater than or equal to the variance of the random variable. Okay, and for a given value xt minus 1. Okay. Then from the definition of Vt, we can think the Vt as sum of gradient of fit xt minus 1 minus gradient of fit x star. Okay, the gradient difference at the current point and the optimal point, plus gradient of fit x star minus gradient of fit x tilde plus mu tilde. Okay, and then I will use this when you have a plus b square. This is always upper bounded by 2 times a squared plus 2 times b squared. Since original vt is split to these two terms, we can upper bound the norm square of vt by sum of 2 times this norm square and 2 times this norm square. Right? So using this, we have this. This is upper bounded by 2 times expectation of norm of gradient fit xt minus 1 minus gradient of fit x star norm square plus 2 times expectation gradient of fit x star minus gradient of fit x tilde plus mu tilde norm square. Okay, so now we just need to, it is sufficient to find upper bound of this and this. Okay, and we know something on the expectation of gradient fit xt minus 1 minus fit x star norm square from this. Since the index it is uniformly random, the expectation of gradient fit xt minus 1 minus gradient of fit x star norm square is equal to 1 over n times summation gradient of fi xt minus 1 minus gradient of fi x star norm square. And we know this is upper bounded by 2 times beta f x t minus 1 minus f x star. Right? And also for this, we also can use very simple trick. We know that the mu tilde is an expectation of, so mu tilde is expectation of gradient of fit x tilde minus gradient of fit x star. Why? The expectation of gradient of fit x star is 0, and from the definition, mu tilde is equal to gradient of fit x tilde. And when we have this expectation, and this is the minus of the random variable that having expectation mu tilde, basically, when you have random variable x and we have a random expectation of random variable x, the expectation of the norm square is always upper bounded by expectation of norm square. Okay, from this, the expectation of gradient fit x star minus gradient of fit x tilde plus mu tilde norm square. This is upper bounded by expectation of fit x star minus gradient of fit x tilde norm square. And again, we know this property from the previous this inequality. Okay. So let's wrap up all thing we have. Then we have this, the VT's variance for given xt minus 1. This is upper bounded by 4 times beta fxt minus 1 minus fx star plus fx tilde minus fx star. This is very nice news. Why? As our point is getting close to x star, the variance of Vt, the variance of our stochastic gradient update rule, is upper bounded by almost 0, because fxt minus 1 minus fx star plus fx tilde minus fx star very close to 0. That is what we really desired, what we really want to obtain. When we can control the variance adaptively and the variance converges to 0 as our point close to the optimal point, then essentially the SGD rule can converge to the original optimal solution without any oscillation, without any perturbation. This is what we really want to do, and that is the power of SVRG. Okay, this simple update rule basically introduce this auxiliary random variable, and this auxiliary random variable can make almost 0 variance when both xt and x tilde becomes close to x star. Okay, so now only one remaining thing is we need to show both xt minus 1 x tilde becomes closer to x star as we iterate more SGD update. Okay,